Hello, it's great to see everyone. My name's Hannah. This is my third year working with the Park Service. I spent my last 2 years working at Great Sand Dunes National Park. So if you've been to Colorado, it's a great place. Recommend you check it out. This is my first season at Capitol Reef. I started in April and I'll end my time there in mid-October. So getting near the end of my time at Capitol Reef. It's been wonderful. We'll look at my evening program tonight, and it is interactive. So while we'll do questions at the end, I will ask some questions throughout, and I would love your participation. We'll start by looking at a map. So this is a map of the general area that we're at right now. What I love about this map is it shows a lot of the geologic diversity in the area. So when you look, you have Glen Canyon, so these deep river canyons, Boulder and Thousand Lakes mountains, and then Capitol Reef, the water pocket fold. There's just a lot going on here. It's a really incredible landscape. And if you get closer on the map, you'll zoom into part of Capitol Reef, the Fruita district, if you visited the park. That star there is where the visitor center is in the campground, where we usually do these programs. But you can see, even as you get closer on this map, there's a lot more to see. Different rock layers. There's actually 19 different rock layers at Capitol Reef, about 280 million years, or billion years of history. Lots of different canyons, different things to see. As you continue on, you can see those. So we've got the Fremont River flowing through. Looks like a storm's just happened. You can see all of the mud in the water and the beautiful rainbow. And then other parts of the park, like the Bentonite Hills, if anyone's been fortunate enough to get up into the North District, you may have seen these gray, purple, and red hills made out of this bentonite clay. And as you continue, at the end of the scenic drive, which is unfortunately closed right now still, you can see the tanks down at Capitol Gorge, which is entirely different sandstone. Looks very different than what you're seeing at other parts of the park. And also the Chenley Formation, one of the really unique rock features here. You can tell it's different from all the others by the gray color, all the red there. It's just a really unique area. And if you even get closer to these rocks, you can see the textures in the clay, some of the calcifications, some of the different solution pockets where there's been differential erosion, the rocks melting away. There's a lot to see at Capitol Reef. But it's not just a geologically diverse place. Even though we look at landscapes like this, that may be one of the first things you think of is how this landscape got here and how there's all these different rock layers. But if you look closer, there's a lot of history here too, a very diverse amount of history. If you've seen the petroglyph panel, the 1,000 to 2,000 year old petroglyphs done by the early indigenous people at Capitol Reef, there's a lot of history there, as well as some of the early LDS settlers in the area. There's a lot of history. If you've been to the orchards, you've been able to experience just a part of their history. And even up in 1971, when Capitol Reef became a national park, there's some early National Park Service history there. But one thing's for certain, all of the generations of people who've been able to live in Capitol Reef have been able to experience the beautiful night sky. They've been able to look at views like this. You can see one of the historic cabins just off of Highway 24. It's an incredible night sky. And the night sky also serves as a sort of map, like we looked at the map at the very beginning. The dark sky pointing to Polaris here, a map for generations, and then also it's been a form of storytelling. All the stories behind the constellations that many different cultures have come up with their own stories for. That's all been part of Capitol Reef's history. And that's where we'll start tonight with our program, Colors of the Stars. So if we move forward, we'll do an activity. So if we go back one slide, I want you to take your thumb and hold it up to this picture. I want you to shout out how many stars you think are behind your thumbprint. Millions. My favorite answer I've gotten is at least one. You'd be absolutely right. So there are countless stars. They say if the universe was a sandbox, what we're able to see from Earth in the night sky is a thimbleful of sand. So you think about a fingertip's worth of sand in a giant sandbox of the universe. And as we continue, you're not just seeing stars, but you're also seeing galaxies. This is an image taken by the Hubble. You may have seen it. It's a pretty famous image of all these different galaxies. And if you could zoom into one of the galaxies, it would look something like this. What I love about this picture, it almost reminds me of the map that we looked at. You see all of these different stars within this galaxy, different colors, shapes. As you zoom in further, it may look something like this. If you could gather all the stars together, we'd have a star chart like this. And we'll start with a question. What are stars? Me personally, when I learn about a new topic, I like to start with a definition. So that's where we'll start tonight, with a definition. And I'll go ahead and read it. It says, a star is a luminous ball of gas, mostly hydrogen and helium, held together by its own gravity. That's a lot of words. We're going to take it piece by piece, and we'll start with gravity. So gravity, we've all experienced it. You may have experienced it today or in the park. If you've climbed up any of the rocks, especially if you've hiked the Cohab Canyon Trail from the switchback side, you definitely have experienced gravity. Or you're experiencing it right now as you sit comfortably in your chairs, or after a long hike and you have the chance to rest. But gravity is really important. It's what keeps us here on the ground, and gravity is a key component in space as well. So gravity in space looks a little bit like this. This is the Cat's Eye Nebula. I think nebulas are incredible to look at, but you can really see gravity at work here. So if we continue, there's a few arrows here that we may have to click through. You can see gravity pulling everything together. The very dense center, that's gravity pulling all of the material to the center of that nebula, where it's the strongest. Yeah, there's a few arrows. That's all good. And so what gravity is pulling together is mostly hydrogen and helium. So we'll look at our periodic table of elements here. I'm sure many of you have seen these before. I promise this won't be a college lecture. But we're going to talk about specifically hydrogen and helium. Does anyone want to take a guess at why those are elements 1 and 2?
Oh, the one proton, one electron thing?
Yeah.
It's just the smallest number of particles within each of those two elements.
So you're right on. So we'll go ahead and move forward, hydrogen and helium. Hydrogen is the lightest, it's the simplest element that we have. And there's one proton and one electron. So this is as simple as it gets. You've got a positively charged proton at the center or the nucleus of an atom. And then surrounding it is one electron. That's how they stay happy, they stay together. And then if we move forward to helium, you can see things already get a little bit more complicated, just moving from 1 to 2. You have 2 protons, 2 electrons, and then 2 neutrons, which just add mass. They don't have a charge like everything else does. If we go back, so we'll look here, this is what happens. We've got gravity pulling everything together, that hydrogen and helium. And at the center, you actually have so much gravity that hydrogen can turn into helium. It gets really hot as well. The center of a star can be up to 27 million degrees Fahrenheit, which is what allows for these heavy chemical reactions. And so those are also causing a lot of pressure. Gravity's keeping everything together. And if we go back, you'll see this periodic table again. Does anyone want to take a guess at what the heaviest element that can be formed at the center of a star is?
Iron.
Iron, you're absolutely right. So iron, element number 26, that's going to be our heaviest one. We'll take a look at iron here. It's much bigger than hydrogen and helium. So you can imagine with 27 million degree temperatures, you can get elements this heavy. 26 protons, 30 neutrons, and 26 electrons is what makes up iron. And when a star is actually forming iron, that means it's near the end of its lifespan too. So when you're getting these heavy, heavy elements at the center of a star, it's actually towards the end of a star's life. As we move forward, that's how you get something that looks like this. And if we go back to our definition, a luminous ball of gas. So we talked about gravity, hydrogen, and helium. Now we'll talk about the final product. And it starts with this nebula. So the Swan Nebula, another one of my favorites to look at. It sort of reminds me of the Chinle Formation at Capitol Reef with all the grays and reds and yellows. Really cool to look at. This is the beginning of a star's life. This is where you get the gravity and then all of those gases coming together. We'll take a look at the star life cycle. So they all start as nebulas, and like us, stars can take many different paths in life, just depending on how hot they get, what they're made of. You can get supergiants, you can get different nebulas, dwarf stars, even stars like our sun. And that all comes from these nebulas. You've probably seen this, the Pillars of Creation. This is a really famous photo taken by the Hubble telescope. And then the Carina Nebula. And so this is a great image of all of those gases coming together to make these stars. And another thing too is you'll notice the stars are different colors as well. So if we move forward to our star chart again, now we know what stars are, so we can talk a little bit about what the different colors mean. So what do these different colors mean? I'd like you to raise your hand if you think the red stars are the hottest. Some nods. Raise your hand if you think the blue stars are the hottest. A few people. Raise your hand if you're unsure. Okay, perfect. So here on Earth, we typically associate red with hot. So when you look at fires, or maybe you look at the red salsa and you decide not to eat that one, we associate the color red with heat. And we associate blue with cold. Think of ice, when you get the frost warning in blue. But in space, it's actually the total opposite. This is the Hertzsprung-Russell diagram, and this is showing us temperature increasing and decreasing, and then luminosity, so how bright a star is, how we're able to see it. So at the top you see we've got our brightest and hottest stars. Those are going to be the blue stars. As you work your way down, you've got your cooler red stars. And so we'll look at some of these closer. You can see these bright blue hot stars. These are where you're getting some of those heavy elements. These are incredibly bright. We can see a lot of these easily in the night sky. As we move down, some of the middle ground, the white stars, often these are white dwarf stars. These are kind of the middle as far as temperature. And then we move down to our cooler stars. And what does this star look like? The sun, yeah, it looks just like the sun. I've got a photo of the sun here for us. Pretty special. Taken, and we have another photo. You'll see this little dot. Does anyone want to take a guess at what that dot is crossing over the sun?
Mercury.
Mercury, not quite.
Venus.
Venus, you're absolutely right. So this is Venus passing in front of the sun. And Venus is roughly the same size as Earth, so it just gives you an idea of how large the sun is. And if we move forward, one more, you can see, compared to the planets down here, how big our sun is. It's the largest object in our solar system. Everything here revolves around the sun. It's crucial to life here. But the sun is actually not that large or important in the grand scheme of things. If we look at this next chart, the sun is that speck all the way at the very end. So you can almost barely see it compared to some stars like Betelgeuse or Antares. There are some stars that are so much larger. Some that are hotter, cooler. There's a wide variety of stars that we have here. And if we continue on, there's also some stars that are much smaller than the sun too. You can have some of these white dwarf stars can even be as small as Earth, which is pretty cool to think about, a star the size of our own planet. But if you take this star chart that we've talked about, what stars are, what the different colors mean, and you combine it with our periodic table, and then also combine that with the star life cycle chart, you'll get something that looks a little bit like this. This is the origin of the solar system elements. This is done by Jennifer Johnson at Ohio State University. And she did a lot of research with her and her team on where we get the different elements from events in space. So all the elements we've talked about, they all come from different things in space, whether that's from Big Bang fusion, exploding stars, dying stars. That's what gives us all the elements that we currently know exist here on Earth. And we'll talk about a few that you've probably heard of. Things like carbon, oxygen, silicon, iron, and calcium. Those all come from a variety of different space events. And they're a big part of life here in Capitol Reef itself. So we'll start with our environment here. You can actually see all of these elements at work. One hike you may have done, if we move forward, is the Hickman Bridge hike. It's a really cool hike, definitely recommend it. It's a shorter one, which is nice. But Hickman Bridge, these beautiful Wingate sandstone cliffs, known for their red color. They get that red color because of iron, and more specifically, iron reacting with oxygen to rust. That's what gives these cliffs their deep red color. And if we also look back at the Chinle, iron's also responsible for the color here. And some of the other colors in the Chinle are due to elements not being able to react with oxygen. So the Chinle was a forested swamp long time ago, and that water covering the area didn't allow for the different elements to react with the oxygen in the air, which is why you get all of these cool colors. Carbon in the fruit that hopefully you've gotten a chance to try at Capitol Reef. We've got some apples and pears available right now to be picked. But carbon's in all living things, and especially the fruit we have at Capitol Reef. And then the black boulders, I'm sure you've seen a lot of. You've got calcium, silicon, all kinds of different elements in these basalt lava rocks that you can find all over the landscape out here. But these are also the elements that make up us as well. From the oxygen and nitrogen that we breathe, the carbon in our own DNA, iron in our blood, calcium in our teeth and bones, we're all made of the same stuff. So when you look at this landscape and you see all these elements at work, you can know that they're responsible from the night sky. We have beautiful views like this at Capitol Reef. Incredible to think of that's where the elements come from. And so we'll start with a question. When you see night skies like that, you may think, what does your home sky look like?
Just like that.
Yeah, it may look something like this, especially if you're from here. Your night sky may look something like this, where you're able to easily see the Milky Way and hundreds of stars, or depending on where you're from, your night sky might look a little something like this. I know for me, this is what I grew up seeing in Fort Worth, Texas. I grew up seeing about 4 or 5 stars in the night sky most of my life until I moved to college at the age of 18. So I had never seen the Milky Way or many stars at all for most of my life. And we have a map here of light pollution. So if you're not from here, you can find your city on here. It's really interesting to see just how bright things are. And this is more of a night sky map of the lights we can see. The light pollution itself can extend further out past these cities. I also have a map of the other side of the world in case you're interested in seeing that as well. It's cool to see how things are dispersed. If we look at Utah, you can see some concentrated areas, especially up near Salt Lake, down in St. George and Cedar City. But if we zoom in closer to Capitol Reef, you can see it's incredibly dark here. And Torrey as well, you can see a small little bit of light, but nowhere near as much as some other places. And so what we can do to protect skies like Capitol Reef and here in Torrey, I would love to hear some suggestions. What are y'all's suggestions for things you can do to help with light pollution?
Shield your lights.
Shield your lights, absolutely right. Anything else?
Have them on only when you need them on.
Only when you need lights on, yeah.
Use a motion detector.
Using motion detectors. These are all great suggestions.
And marry the mic.
And so we know some things we can do from an organization called Dark Sky International. That's actually the organization that gave Capitol Reef National Park their gold tier dark sky designation. And they're responsible for monitoring dark skies all over the world. But they have a lot of educational material. So if we look forward, they talk about what light pollution is and how it affects us. So light pollution, is light in the atmosphere blocking our vision of the night sky. But it not only blocks our vision, but it also affects a lot of other things, such as destroying critical wildlife habitats. One thing I heard from another ranger is the dark sky is a habitat. And I hadn't thought of it that way until I heard them say that, but for some of these nocturnal creatures, that is their habitat, like a forest or a desert. And then inhibits scientific research, robs us of our night sky heritage. So how we talked about some of the earlier people here using the night sky for storytelling or as a map. We're using less of that nowadays, especially in areas where there's so much light pollution. We're not able to continue those things. Wastes energy and money. This is usually everyone's favorite. When you turn lights off, you do save money, which is great. Decreases safety and security. Often glare from all the lights decreases what we actually can see in the dark. And harms human health. I'm sure you've heard of a circadian rhythm. Having dark skies and turning lights off actually helps us stay on a good sleep schedule and stay healthy. And so they also provide lots more educational material that's also accessible to everyone here. If you go to their website, these are all things you can access, share with your friends and family. But they give us advice on how to use lights and sort of things you've already said, like only using it when you need it, shielding light, pointing it down, using amber light instead of bright white light. That also helps. And then we also have just examples on how this helps. So you can really see how that light pollution is brought down. Light pollution is one of the easiest forms of pollution to fix. There's no residency time in the atmosphere. When you turn the light off, that light pollution's gone, which is really good to think about. And often, a lot of times, people think that you can't do much, especially if you're from a large city. It's easy to turn your own lights off, but sometimes that may not help. And that's not necessarily true. Something that happened in Fort Worth, where I'm from, is they did this campaign called Lights Out Fort Worth, where certain times of the year, actually the entire city of Fort Worth, including the skyscrapers and things like that, will turn their lights off to help with migratory bird migration. So that's something that a large city has done on a large scale to help reduce the impact of light pollution on the environment. And it was great. You could see more stars in the sky too, which is really awesome. And that's what allows us to see views like this at Capitol Reef and here in Torrey and the surrounding areas as well. I'll go ahead and leave you with a quote. It says, "There's as many atoms in a single molecule of your DNA as there are stars in the typical galaxy. We are, each of us, a little universe." So thank you all so much for coming.
So we're open for questions. You can go to the mic to the right of John or put your comments or questions in the chat function. Feel free. Go now.
I actually haven't seen that Pillars of Life painting or picture, whatever that was before. Could you talk about that?
So it's a nebula. That's where stars are forming, and that's what that nebula looks like. I'm definitely no expert on why it looks like that, but it is really cool to take a look at.
I really first saw the Milky Way about 50 years ago when I moved to Colorado up in the mountains, and it was just so stunningly bright. Now that I'm down here, it doesn't seem quite as bright, even though we're in a dark skies area. So is it something with the environment, or is it I'm not getting as much light into my eyes anymore as I age? What would you say about that?
Yeah, it really depends, especially depending on where you're at. Air quality has a lot to do with visibility. Especially recently, we have had a lot of smoke in the area. When you're in town, sometimes even just small things can affect the air quality quite a bit.
Are you aware of any measurements of the, absolute or the measurable intensity of the Milky Way over the decades from various points?
Yeah, I don't know enough about that, but it would be something really interesting
Might
to
be something.
research.
So just a comment about our own dark skies here. I have seen my shadow
from the light of the Milky Way.
It's awesome.
A wonderful presentation, thank you. I wanted to ask, are you aware of any archaeoastronomy sites in Capitol Reef or in this vicinity?
I'm not. That's not saying that there aren't. I just probably haven't been made aware of it. A lot of the archaeology sites are highly sensitive, and most of us, I work in interpretation, we don't even know about a lot of them. So.